ಕರೆಕ್ಟ್ 9ಗೆ ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತಿದ್ದಾರೆ.
Good morning, dear participants. Sorry, today the session is a little bit early uh, because of the time constraints of the resource person. So we have to start by 9 o'clock and we have to complete as early as possible. Here we have here with Mayank Joneja as a module lead at Edge Applications at Viman AI Limited, and uh, hope I'm audible.
Yes, I can hear you.
Yes, sir. Now, Professor Chetan will introduce our resource person.
Very good morning, everyone. Mr. Mayank Joneja is currently working as a module lead edge applications at Viman Robotics Private Limited on camera-based solutions for the warehousing and logistics sector. Previously, he has worked on thermal camera products for commercial applications, including vehicular autonomy and facility monitoring. He has a master's degree in embedded systems and ICT innovation with a minor in entrepreneurship and innovation from TU Berlin, Germany, and Aalto University, Helsinki, Finland. Mr. Mayank completed his bachelor's in electrical and electronics engineering from BITS Pilani, Goa in 2015, and his interests are in building and flying drones, playing the drums, and also enjoys photography. We are very happy to have you today, sir.
Thank you.
Hearty welcome to you, sir.
person consider ನೋಡಿ
Slide I can note.
Joneja, sir.
Thank you. Thank you so much for the warm introduction. Let's start now. And if
Yes,
you
sir.
could please help with muting participants as they join, that will be great.
Yes, sir.
Sure, sir.
I'll
Sure.
just start with the slide. So can everybody see my screen?
Yes, sir.
All right. Good morning, everyone. Hello. And today we are here to understand what does it take to make a robot in 2023. I'm Mayank Joneja. I am the module lead of Edge Applications at Viman.ai. The agenda for today will be to briefly walk you through some things about me and my work, go on to field case studies. Then we shall discuss the system architecture of modern robots. I'll also walk all of us through an example system architecture of an autonomous drone. Then going in with the theme of the overall sessions, we will try to understand where does artificial intelligence fit in. And then I would like to end with very concrete recommendations of some tools and recommendations for projects that we can use. And we'll have a question and answer session at the end as time permits. Otherwise, I would encourage everyone to drop questions in the chat so we can address them in the end.
Recording in progress.
All right. So about me, as I mentioned, I'm the module lead Edge Applications at Viman. Before this, I was a senior software engineer focusing on robotics and firmware at Viman.ai. Prior to which I was working on firmware and embedded Android systems at Tonbo Imaging. I'll gloss over this because it's already been there in my introduction. But yeah, this is what I do for fun. I build drones like these where I can fly them first person view, have goggles strapped to my head and see what the drone is seeing and then fly them. And I also assemble the components and select them and build it from scratch. So I'd like to quickly share a video about what Viman does to give you a sense of what are the kind of products that we work on. So we primarily work on camera systems to make lives easier in warehouses for inventory management. And it has a lot of overlap with robotic systems because of the software stacks we use and the overall system architecture of the products. But strictly speaking, right now, our camera systems are either stationary or driven around by humans because for the conditions at which we operate in, it is a lot safer and also cost effective for now.
Viman is proud to announce the next giant step in automated cycle counting, StoreTrack. StoreTrack provides the safest, most efficient, and longest continually running cycle counting automation capability available on the market today. StoreTrack is an industrial strength mobile vision system. It's easily lifted and handled by existing forklifts, order pickers, or other material handling equipment to scan and capture inventory from the floor to your highest shelves. Operators receive their cycle count missions through the StoreTrack Task Manager. These missions can be highly specific to individual bins or as broad as cross sections of the entire warehouse. The Task Manager details exactly where the operator needs to go and even keeps track of individual cycle count tasks in real time. StoreTrack includes laser positioning guides to help operators position the cameras in the appropriate starting position. Once the lasers are aligned, StoreTrack starts to scan. StoreTrack includes several cameras and sensors to ensure the widest field of view possible. More than just a barcode reader, StoreTrack reads all the areas of the label important to customers.
Yeah. So as I've shown here, we have systems which help us read all the label information on these packages to help manage warehouse inventory more efficiently. So what does the job actually look like? The media says I'm building robots to destroy everything. My friends think I'm building robots to fight. The customer wants me to build a full robotic automation cell. What my boss thinks I do, what I think I do, clearly from my t-shirt, like I'm building Iron Man. What I really do is sit with a laptop next to a robot debugging. So we have systems here in our Kormangla lab where we are mimicking the warehouse products that we have. We can see conveyor belts or warehouse setups with boxes and labels that we test our computer vision and AI algorithms on. And overall, what the split looks like is that we spend a lot of time understanding what we have to build and how, and also why. And then reading and reviewing code to help others becomes a significant part of my job as a senior developer or now a module lead. 20% of my time is spent on building things and also 20 on project planning and thinking and helping others plan. So I lead the groups for embedded machine learning here at Viman, as well as the localization group. And yeah, these are the kind of things we end up doing to build the robotic systems that we build. Okay, now let's jump into some cool case studies because I didn't want to go through a textbook definition of a robot. I rather wanted to show you what robots can look like because quite often people imagine robots to look a certain way, but all of these examples that I'm going to share here are now actually robots, which we can see in the wild. So in general, there is this notion of the 3Ds or the dull, the dirty, and the dangerous tasks, which are too boring or too messy for humans to do or too dangerous. Those are the ones for which robotics is best suited. And let's just walk through a couple examples. So what we saw was Spot by Boston Dynamics and how it's used for industrial inspection and a lot of the important characteristics of what go into building such a system nowadays. Yeah, I'd also like to show an example of a flying robot. Yeah. So that's the Skydio 2 that we saw, which is a personal cinematography drone, but they also build products for the military and for similar industrial inspection and other use cases. Closer to home, there is a company called Nimble in Bangalore, which is making cooking robots, which look like a portable kitchen appliance, which can help cook one-pot meals. We have these in our houses nowadays, which is basically vacuum cleaning robots, which became increasingly popular in the pandemic. And yeah, so they have actually started coming into our homes as well with autonomous or semi-autonomous agents. Regarding drones, there is enormous opportunity in domains like delivery of medicines and supplies, like what Zipline does. There is inspection of facilities and gas pipelines and highways, which is a common use case. There is delivery from Swiggy and Zomato, which is on its way and will happen maybe someday soon. Yeah, in India, Maruti Drones and IdeaForge are two big companies which are doing things like day and night surveillance for defense and border monitoring. There is weedicide and pesticide spraying, killing mosquito pools in urban puddles, and killing even crop-eating locusts in the fields. We've also had companies help out with announcement in slums during COVID with mounting a speaker on the drone. So those are the case studies I wanted to quickly highlight before we move on to understanding what is the system architecture of modern robots. And yeah, maybe drop your comments in the chat onto why you think this image is here, but I think we'll slowly realize as we go into this. So let's start. So how does a robot work? There is this classical paradigm of breaking down autonomy into a sense, plan, act loop, which basically means you have environment perception, then decision making, and then actuation or motion to encode the behavior or the functioning of a robotic system. So sense is there is a wall in front of me. Plan is I should probably move away and not stick to it or bump into it. And the act part would be move back by 4 centimeters, for example. So let's drill down on each of these components and see what it takes to do the sense part, the plan part, and the act part. So For the sense part, we have a sensor suite to sense the environment, features, distance from objects, position with regards to the world. So you could have cameras on board, you could have a laser detection and ranging module, you could have the same using a radar or radio. You could have intrinsic sensors as well, such as an IMU, which can help it track its acceleration, angular velocity, and heading. Or you could even have a GPS on board to figure out lat long and velocity and height. So that would be the raw sensor data coming from this suite of sensors on your system to tell about its state in the world. But that is just the first step. The next part is usually perception, which processes this raw sensor data into actionable information. So you need to use all these inputs, do sensor fusion, and localize yourself or map your environment. Where am I? What does the environment look like around me? So that would be localization and mapping. Then you could have obstacles. As you're moving from point A to point B, you don't want to bump into things, topple things, or collide. So obstacle detection becomes an important part. And in doing so, there might be some dynamic objects in your scene as well. So there could be people moving around in the same facility. And if you could predict where a person is going by tracking how they are moving, you can make better informed decisions about whether you should pause, stop, turn around, or take another path while you're moving. And of course, based on this perception information, the next step is usually route planning, behavioral planning, like I mentioned, or trajectory planning. So deciding what to do, whether to stop or to go, what route you should take, whether you should continue on the same trajectory or not. And then the final part usually ends up being the actual actuation. So you want to move a certain way as dictated by your behavioral planner, which could mean opening a door, lifting a box, flying to a certain location, and leveraging technologies like PID loops or model predictive control for your controller or inverse kinematics for positioning your end effector in a certain way and then grasping to grab onto something. So how does all this actually happen when it comes to the hardware software layers of the overall technology stack? I want to present a basic high level system architecture and then walk through each of these layers that you see here. This is a broad generalization as a framework to help us understand these incredibly complex hardware software stacks. But the specific implementation from one robot to the other could definitely deviate. Also, the definition of what comes under firmware, what lies in middleware can often get very fuzzy. But I did want to present like an overall component by component or layer by layer architecture so that we can at least understand the general ecosystem in each of these layers and what that actually looks like. So if you haven't guessed by now, I keep mentioning layers and how we're doing this because in embedded systems or in usually in our technology stacks, we like to build upon layers of abstraction as well as have interfaces between isolated components, and hence the hint about the onion where we are now going to peel the layers and understand what's happening inside each of them. Let's start with the hardware. So what does the hardware for a lot of these robots look like? Usually nowadays, there is a very common starting point of a dual processor architecture where quite often you have a microcontroller which is helping out with some sort of an autopilot or a bare metal program or a real-time operating system running for the actual actuator control part, like for controlling motors, LEDs, other end effectors, as well as grabbing data from low-speed sensors. So I2C or SPI. And the second processor is usually an application processor, which is running embedded Linux or Windows on an x86 or an ARM64 platform with an ARM Cortex M or an R series for the MCU, like I mentioned. But high-speed peripherals over USB, MIPI for cameras and displays would, or even things like Ethernet, would usually be connected to this companion computer. And you would have like cameras, lidars connected over here, and the accelerometer gyro could be either on the MCU or here, depending on the overall architecture. And you could have these two processing units talking to each other over UART or CAN bus or Bluetooth. And of course, none of this works without power or mechanical elements for mounting, enclosure, and things like thermal management, which are all aspects which are extremely, extremely important for the sane functioning of this entire processing stack. So that's what the hardware layer looks like. Now let's go to the firmware layer. What does it actually mean to have firmware on both the embedded Linux host as well as the low-level MCU? So we basically have drivers for the low-speed sensors, like I mentioned, using I2C, SPI, UART. And on the embedded Linux front, we might have camera drivers for MIPI, CSI, or USB. There are hardware abstraction layers for the higher layers of software to talk to everything underneath. And like I mentioned, on the MCU side, you could have a real-time OS with its own HAL and a bare metal embedded C implementation as well. And here in the image, what you can see is basically how you have a camera, how it talks to the hardware on the SoC. And then over that, in the kernel space, you have the IPU, CSI, and camera drivers, which in turn talk to video for Linux or V4L2. And then in the user space in our applications through IOCTL calls, we actually get the frame. So this is the basic firmware stack that it takes to fetch an image from a camera sensor using the processor or your application SoC and then presenting it to the application layer for software, which further processes these images. So for those of you familiar with OpenCV or similar programs, when you do an IM read, these are often all the things that happen behind the hood to fetch you that image from that single camera. Okay, now one layer above the firmware layer, like we mentioned in the original model, was the operating systems layer. Now, this is where the embedded Linux, or for the case of NVIDIA embedded GPUs, the NVIDIA Linux for Tegra board support package kind of layer comes in. For Snapdragon chipsets, we have the Android open source project, which serves a similar function. And this basically ends up being libraries for applications, tool chains, low-level APIs, development and debugging and profiling utilities, which all get packaged along with some custom kernel modules, as well as the bootloader to form the BSP. And this is what we talk about when we talk about the OS layer to help get information from our sensors to higher layers and also efficiently process things using computer vision, AI, multimedia, and graphics applications. So the toolkits which help out with all this, or the basic root file system, all of these user space drivers and the tools for checking how fast things are, how much CPU, GPU, RAM, how things are scheduled, all of that comes in the OS layer and then the BSPs. So what is the middleware then? The middleware is basically things like inter-process communication mechanisms on top. So if you write your application, usually we don't prefer to write it as a monolithic single piece of code. We would have it be multiple applications which run as their own processes talking to each other. So the middleware layer or the infrastructure software, which helps these processes talk to each other, becomes very important. So you might have blocking or non-blocking remote procedure calls, a publish subscribe kind of paradigm. You could have distributed application launch mechanisms for each of these user space applications. You would have utilities for monitoring and logging, as well as support for writing your user applications in different languages, C, C++, Java, Python. So these all are given by the middleware framework. And one of the most common ones nowadays is the robot operating system, where the name might say operating system, but it's actually a middleware or a framework, which, as you can see in this diagram, kind of comes on top of the OS layer of Linux or like Linux, Windows, Mac or an RTOS, where the older version ROS 1 had its own middleware implementation with a client library, TCP ROS, UDP ROS. But the newer one actually relies on industrial grade DDS layers for the industrial grade standard middlewares and provides abstractions on top of it so that the nodes that we run on the application layer applications can actually leverage all of this infra, and you can focus really on what the end application is you want to build and not worry too much about writing code which talks between these nodes, so that the infrastructure is there and you can really focus on doing what is important to you at the application layer. So we've covered hardware, we've covered firmware, we've covered OS on top of it, middleware, application. So now let's get to what the application layer usually looks like. One of the most common things to do on the application layer, as you can see in the image for like a self-driving car example, is perception. So you have computer vision and deep learning, which is running. You have some custom application nodes to help out glue everything together. You have the navigation stack, as well as behavior trees for the decision making. So your sense, plan, act, as I mentioned, you have perceive. So the perception part, the actual software for that runs here. The planning part runs here, and the act part of at least the high layers of how you want things to move a certain way will run here. What that means in terms of specific pulses, currents, or timings for controlling the motors is handled by the lower layers or the MCU. But the fact that you want to trigger an action a certain way will happen at the application layer. Now that I've given you an overview of what an abstract system architecture looks like, I just wanted to kind of highlight how when we talk about robotics engineering nowadays, as per LinkedIn, it's usually the application layer which is given the most amount of weightage. It'll usually be navigation or path planning, localization mapping, control systems, or computer vision and deep learning, which means if you go for getting a job as a robotics engineer, it's usually all software engineers focusing on different aspects of moving autonomous agents. But is that all that it takes to build a robot? I would like to contest no. Individuals rarely build such complex systems. There is the need for an electrical or an electronics hardware engineer. There is a mechanical engineer, a firmware engineer, navigation and autonomy engineer, which I mentioned as a robotics engineer in the previous slide, a full stack, front end, back end software engineer, UI UX designer, DevOps, and a lot of other interconnected roles. Because quite often customers will not pay you for just having a cool complex system in their facility. They would want something like inferences or insights that you can draw which are actionable. What can they change in their processes that they are doing wrong in their facilities, which can help them save money? And to present all that, you usually have a dashboard, a lot of software wiring, talking to their backend systems to check on certain things. So you need all these people and teams to actually build an end-to-end robotic solution. The navigation and localization and all the cool-looking application layer things are usually just the tip of the iceberg. All right. So now let's get to an example architecture. We walked through an abstract architecture, more or less. Let's try to see what that looks like for an autonomous drone. So the drone we have here is a Holybro PX4 vision platform. What it basically has is a frame where you mount everything. It has a flight controller and electronic speed controllers, which are what drive the motors. The flight controller is the microcontroller in this case, the MCU, usually an STM32, F7, F4, those sort of ARM Cortex M chips, which also has an integrated IMU on the board, and it runs something called an autopilot. I'll get to that. And for the frame, the drivetrain, which is battery, motors, props, and the flight controller and ESC help to keep the drone in the air and fly around. But it is the companion computer with cameras and optical flow sensors which actually brings the autonomy part of it. So flying from point A to point B on its own, that happens through a companion computer. And you have sensors such as a GPS with a compass on a mast you can see here, as well as like a 3D camera, which is in front. Yeah, so that's what it takes to build an autonomous drone. And on the firmware and control software, you would have something like PX4 Autopilot or ArduPilot. So Writing the Kalman filter or the PID loop to actually control the motors, that's a solved problem. And there are open source implementations which help you out with all of that so that you don't have to worry about the low level flight dynamics or worrying about how to keep the quadcopter in the air. We have these complex autopilots which are thankfully available to us all openly, which can do sensor fusion for flight using the accelerometer, gyroscope, and compass on board. And also some rudimentary autonomy is provided by things like ArduPilot Mission Planner, where you can have it go from point A to point B. We have micro ROS or a UART-based communication. So this flight controller must now talk to the companion computer running the autonomy stack, right? So that happens through something called a Mavlink protocol or Mavlink messages, or you can have these micro RTPS new topics which allow communication between the two. Additionally, you have a telemetry link to a ground control station so that you can monitor the drone from your laptop, as well as mission execution using the GPS and compass on board. So this was the firmware on the drone or the autopilot. And here what we have similarly, as we go up the layers, we have a ground station application stack. So your UI would look like this. You have this software called Q Ground Control, which has Linux and Mac support. AX4 autopilot system, but it helps basically get information from the drone to understand if everything is okay, it's safe to take off, if all the sensors are functioning. You plan out a mission from point A to point B, and then you can take off from here and let it go and do its thing. And the companion computer would usually be running mission level autonomy. So if you have complex vision processing for things like obstacle avoidance, dynamic object tracking, like I mentioned, SLAM, so simultaneous localization and mapping, or behavioral planning, all of that would go on the application or the companion computer and usually implemented through a framework such as the robot operating system or ROS. Okay, so a lot of heavy stuff. Where does AI fit in? So robots are essentially embodied artificial intelligence. There are several places where AI today actually helps with all these different aspects of the software stack or the behaviors in the robot. The first or the most obvious one is perception. Once you get frames from your camera, to do object detection, we have increasingly deep learning based models, which can help us do that. We can do semantic segmentation so that we can understand the scene to see where is the road, where is the sidewalk, where is the person. Uh, Also for path planning, so you understand that, hey, this is the road, this is where I have to drive. There can be trackers for humans or moving obstacles. So perception is one of the largest areas where deep learning or AI is used. Decision making itself. So there is an entire domain of reinforcement learning, which uses deep learning inside, which is about selecting an optimal policy of actions given a particular state. And then there is also cutting edge work on end-to-end control loops, where let's say if you totally do away with this idea of sense plan act and having decoupled software modules, what if you can map directly from pixels to motor commands? And that is also an active area of research. So coming to tools and recommendations for projects, just to give you context, I wanted to show you all my college robot from 2013. So it broadly follows the same architecture. There was a companion computer in the form of a Raspberry Pi. I had an Atmel AVR based board for the microcontroller. The power that I had was a lithium ion battery with a custom power circuit. Those DC motors for the actuators. I had a 1080p webcam and a light dependent resistor as sensors. And on my ground station, I had built a web application where I could see the live feed of the robot, drive it around with the keyboard if I have to. And also, I used OpenCV on the laptop side to drive it around using gestures. So that was just a basic what I built, but we have come a long way from there. There are a lot more options, both in simulator, which are openly and freely available, as well as real hardware platforms that we can use for our research and projects. And I wanted to now present those here. So how have things changed in 2023? I've mentioned ROS a couple of times. The Construct is this amazing platform which has an integrated IDE a command line terminal, and a simulator environment, 3D simulator, which can help you learn robotics. So with curriculum, it's a paid online course, but the ROS Development Studio, I think, is available for free to try out. And it's a great place to get started if you don't want to set up ROS on your machine and you just want to try things out and learn basic fundamentals of using ROS with C++ or Python or specifics of security or navigation. That's an amazing resource. There is the NVIDIA ISAC sim as well, which is from NVIDIA and is a more graphics heavy simulator, which helps you basically build your robot and try things out in simulation without having to physically construct and run your algorithms in the real world first, which might be either very challenging or also in some cases impossible. Like it's probably not easy to get access to a 20,000 square feet warehouse for everyone. But you could take your robot, try it out in some basic environment in your lab, and then in simulation replicate the same robot and see how it would ideally perform in such a large environment. Um, for computer vision or deep learning to get started, I would highly recommend OpenCV with Python and deep learning frameworks such as PyTorch and TensorFlow. I would like to point out that Python is best suited for quick proof of concepts at this layer for computer vision. C++ is there, but it is really good for performance sensitive applications. The learning curve can be steeper, and there is a lot of scope for spending too much time in memory issues or incorrectly or badly implemented things. So safe, quick, and dirty prototyping, I would always recommend Python with OpenCV, whereas I honestly have experience with like all of these languages, C, C++, Python, but that's how I feel is the lowest friction path to start with projects. Hardware and compute boards. So NVIDIA Jetson is a series where they have these embedded GPUs, which are really powerful devices, which can give you access to CUDA-based GPU programming, a framework called TensorRT, or basically running all this perception and AI stuff that I said at the edge in like a 20-watt computer, which can be mounted on a small form factor robot and open the doors for embedded computer vision or embedded Linux for you. On the microcontroller side, STM32 Nucleo is what I would recommend. There are Arduino or Adafruit microchip boards as well, but in the industry for reliability, the STM32 series ends up being a lot more popular. Specifically for flight controllers, uh, the STM32 along with very nice inertial measurement units or IMUs is packaged in this Pixoc derived flight controller called the Cube Orange. They run FreeRTOS, Zephyr OS, or other real-time operating systems, or you could even do bare metal programming with the STM32 Cube MX HAL and get started. And this will allow you to basically learn how to interface with low-level peripherals such as electronic speed controllers for motors, directly DC motors, or communication over very long distances for serial communication, or things such as I2C temperature, IMU sensors, or other sensors. If we don't want to work at the board level, there are also platforms which exist. One disclaimer I want to give is that availability and procurement is always a pain. The platforms I present here are based on my preliminary searches on availability in the Indian market. And these are typically platforms which are very popular in the research community at the top robotics conferences like ICRA, IROS, and so on. The thing I would like to recommend is to always favor platforms with the most amount of ecosystem support and openly available resources for ease of development over other metrics like cost or complexity or features that you think are too attractive. Because when you actually get down to building stuff, having that ecosystem of support can mean the difference between getting something done in 2 days versus 2 months. So it is really important to have something which has a lot of ecosystem of support, has libraries, examples, a forum, community that can make or break a project quite often. So for drones, there is this small 27-gram drone called Crazyfly 2.0 by a company called BitCraze. It has only a microcontroller and limited compute, but it is a very good platform to start with aerial robotics. And it has basic autonomy add-ons for things like optical flow to see how you're moving and to have some sense of autonomy, or external positioning using markers. They even have like an AI add-on board for increased computation with a small low resolution camera on it as well. Yeah. Um, for ground robots, the JetBot is like an open framework and a lot of vendors sell it, but this is a Jetson Nano based platform, which has increasingly become very popular. And we can use this to run ROS and with cameras and a LiDAR, as you can see here in the image, to try out a lot of these basic SLAM or navigation algorithms and a lot of the things that I mentioned in the previous slides. Another platform which was really popular is TurtleBot, which started off in ROS1 as having a version which had a full laptop inside and has slowly evolved into a much more refined product with a huge sensor suite and amazing actuators. The only problem is availability quite often, but I wanted to throw it out there because often in simulator, one of the most popular platforms you see is still the TurtleBot. There's also an Indian company called BotSync, which has a platform called Volta, which is available for learning and for research. And yeah, that is the end of my presentation. And I would like to now take questions from all of you and comments about how you felt about the presentation.
Dear participants, any questions or queries? Joneja sir, can you please look at the chat box? One question.
Yeah, I saw this question to demonstrate the simulator tool.
Yes, sir.
Give me a second. I will try to fetch out a video. I do have a video. Just give me 1 second. So can everybody see my screen and this video?
Yes, sir. It is visible.
Here you can see this is code written for ROS and C++, where I'm writing a service client to move things around. And yeah, I'm following the lectures here and I'm moving stuff, and you can see this robot in simulation moving around. That's a very quick simulation, but yeah, you could have your own robots and flying robots as well as ground robots in simulation for Gazebo for ROS as well. Any other questions?
Sir, I have one question.
Yeah.
Sir, shall I use this type of robots to find out there is a damage in the water sewages or any other different drones are there?
Yeah, so I had mentioned this company called Flyability, which I believe is based in Switzerland, if I'm not mistaken. You can have a look at their product. They use it for, just give me a second, I'll go back in my slides. When we're going through case studies, you might have seen this odd looking drone. Can you see this one in the top right corner? This?
Yes, sir.
Yeah, so look up this company called Flyability. They have a drone in a roll cage. This is basically a carbon fiber mesh kind of structure which allows it to fly around without bearing the impact of collisions. And they actually demonstrate how this can be used for sewages or for going around in tight tunnels and things like that. There are also several companies which have wired ground robot kind of machines which are increasingly used for clearing blockages inside sewage. So you could look up those kind of machines which don't necessarily fly inside the sewage because it might be like too tough of an environment, but can go down pipes and inspect certain things as well. Yes, but it is possible to do that, yes.
Sir, shall I get any drones like snake robots?
So
Snake
your
robot.
question?
Actually,
get a sleep.
yes, there is a possibilities of T shapes or curve shapes and all, like bends and all there, no, sir.
Yes,
If this type of drones are not able to move all the directions,
correct.
at the time, is it any possibility to construct like snakes or something like uh, movable with the curves and all?
Yeah. So, honestly, whether or not the drone can navigate the curve would be a function of the size and how tight the turn is, and maybe even pilot skill. But it would also come down to things such as battery endurance or communication, which I think will be a much bigger challenge for you than sheer maneuverability. Because as you go deeper and deeper, having access to a remote control station with such a challenging environment for RF can be a bigger issue. And the battery life, if it only lasts you, let's say, 20 minutes and you want to run a 1 hour operation, you are much better off having either a tethered drone which has a wire coming out and you're somehow feeding it power, or you have like a ground robot with a battery and a remote link which is connected over like a wired system. So the actual means or the mechanics of movement, I think, are one aspect of the problem. There will be all these other challenges about communication back to the ground station, and yeah, endurance of the platform itself and how much runtime it gives you, which also come into this discussion.
No, sir. Actually, we done a project regarding the drones, like snake robot.
Mhm.
But thing is, during the construction, it has to move around the 360-degree angle, because if
Mhm.
any tunnels and all there is, it is not in a direction of straight always.
Mhm.
Sometimes it curves, sometimes it may be having up direction, low direction, or left and right. That
Mhm.
has to take a decision and it has to move.
Yeah.
Is it any possibility to construct a drones like snake robots?
Yeah, of course,
Is
there
there
are.
any company that will support that constructions from your
I'm
side?
not. I'm not aware of people who directly offer such platforms. This would be a domain-specific thing which you will have to look up. That's not to say I've not seen snake-like robots being made in universities in the US. I'm not sure if that is the best place to start, though. What I would highly recommend is look at sewage cleaning robots and companies which offer robotic pumping of sewage. See what is the mechanism they use, and maybe what you can do is, because you want to do inspection, just add the autonomy or the computer vision part on top, so that you're not addressing all these problems at once. You already have a platform which can easily maneuver and go down these sewages and handle these parts, right? And you just focus on the task of inspection or adding a camera which can automatically do things which that company might be doing right now through humans. They might have a person on the other end which is looking at this footage and trying to analyze. If you can just solve the perception or that analysis part of the problem, then you don't have to worry with the system complexity of everything. So I would really look at robotic sewage cleaning solutions which are available nowadays. And yeah, there will be some companies for them. I don't know the names of these companies off the top of my head, but you should look that up. I can see a
Thanks.
question here. Yeah, welcome. Sir, could you please suggest some platforms or courses for students which are like package for beginner to have strong basics in AI and robotics, also which are free or nominal? We can get courses, but they'll be in bits. Most won't know what next after the course. Hope I'm clear. Yeah, so Nazim, the problem is that the only course I know is a paid one where you can kind of see if you want to pool in with multiple students and access through a single Gmail account, I think, and or get one for a class and try it out. The Construct Sim was one which I recommended and also showed here. I haven't come across any other course which helps you out with a hand-holding kind of way, but you could, like you've mentioned, look at YouTube tutorials and all that. But the problem of fragmentation is very real. I acknowledge that. Um, you could look at tutorials and which are available to try and build for a very specific problem. When you're saying that you don't know what to do after the course, what I would recommend is maybe if you are fluent in some amount of C++ and Python and have some idea about what parts you'll use, pick up a project. Try to solve a concrete problem statement. and build a very simple robot which can go from point A to point B. The reason I showed my robot was because I wanted to show how I just wanted to build a remotely operatable live streaming kind of robot at that point. And when you try to solve a specific problem and look for coursework which can help you gain the skills you need for that problem, you'll be much better off. In the end, you might not even end up solving that problem, but just having a goal, working towards it, and working on the technologies or the software for that will teach you a lot more than going through a course which does something in simulation and then you forget all that. So, because you will be a lot more motivated, also a bit more frustrated with the actual challenge that you're working on. One good avenue for that usually ends up being robotics competitions at colleges here, and that could be like a great place to start. So you have a concrete problem statement, or you could simplify it and come up with a simpler project that you want to build for your own amusement. It could be fun, or for something practical you're trying to solve at home, and build such a system. Yeah. I hope that answers your question. You're welcome. Somebody's asked me, sir, design of drone. So what we saw here was actually a design of a drone. If you want to go into specifics, maybe you can connect offline. I should also get to that slide. Yeah. So if you want specifics of how a frame, ESCs, everything comes together, you can directly leave me a message on LinkedIn, and we can get in touch. But I didn't want to get into the nitty-gritties of all of it. But the slide I showed about the hardware system architecture, broadly, that is what it will follow. So if you understand this architecture, this is basically what you'll end up doing. For the drone, just the flight part would be the lower part of this. Let me switch to the laser pointer. Yeah. So this part with the power supply mechanical, this would be just the basic drone part of it. So you would have an autopilot MCU, you would have motors which are mounted on a frame, you would have ESCs, and then maybe some sensors on it if you want, and the battery which will hook up, and other mechanical elements, in this case being the frame or straps and things like that, or standoffs and screws. And that is what it would build the drone. If somebody is interested, I could actually show you what I have here. This is my drone, and this is what it would look like. The flight controller board is inside. You have a camera here for first person view. There are wires which are going to the motors. These are the motors with the propellers. I have a GPS module in the back. There's one antenna for video transmission and a video transmitter. I don't know if I can show you this clearly. Yeah, here. But yeah, this is what the overall architecture would look like of a drone. Yeah, any further questions?
Any other questions or queries, dear participants? Okay, Joneja sir, shall we wind up?
Sure. Thank you for the opportunity and also the questions. I hope you gained something or got a bit more clarity and a bit more inspiration to build these complex systems. And yeah, I look forward to staying in touch. Do reach out for any questions or doubts you have.
Dear colleagues and participants, we extend our heartfelt appreciation to our esteemed industry expert, Mr. Mayank Joneja, for joining our faculty development program and sharing invaluable insights on what does it takes to build a robot in 2023. Your expertise and knowledge have been instrumental in broadening our understanding of this cutting-edge field. Your presence has ignited our curiosity and inspired us to explore the future of robotics. Thank you very much, sir. On this
Thank you.
Engineers Day, let us not only express our gratitude to our distinguished resource person, but also extend our warmest wishes to all the engineers participating in this faculty development program. A happy Engineers Day. Dear colleagues and fellow engineers, your dedication to innovation and problem solving is shaping the future of the technology. Together, we strive to advance our knowledge and skills, and today's session has been a testament to our collective pursuit of excellence. Once again, thank you, Mr. Mayank Joneja, sir, and best wishes to all the engineers here today as we continue to drive progress in our respective fields. Thank you very much.
Thank you. Happy Engineers Day. Thank you.
Thank you, sir. Thank you very much.
Bye-bye.
Dear participants, the afternoon session will start at 3:45 p.m. We have two resource persons today in the afternoon session, Mr. Santosh and Mr. Sampath Kumar. Please join the session at 3:45 p.m. And it is an exciting session on 5G and artificial intelligence. Thank you.
Thank you so much.
Feedback link will be shared on the chat box and as well as in the WhatsApp group. Kindly fill up the form and submit at the earliest. Thank you very much.
Recording stopped.